Alkanes have more chances for those H's to bump into one another and to interact with one another. So what's going to have a higher boiling point, methane or octane? What requires more energy to break the forces up? Careful. Okay, let's start from the beginning. Okay, which one has stronger forces holding it together, methane or octane? Octane has stronger forces. So which one requires more energy to break up the molecules into individual? Octane, okay? And so which one's going to need to be heated to a higher temperature? Octane, therefore the higher boiling point belongs to? Octane, good, okay. Where's the cutoff at, by the way? You have methane, that's obviously a gas. Ethane is a gas. Propane is a gas. But you can liquefy propane. Okay, you can kind of force it. What about butane? Any smokers in the room? Right, if it's sealed up inside of a lighter, it's going to be a liquid, but the moment you pop that open, it's going to be a gas. So right around butane and pentane is where we start getting enough of these van der Waals interactions to hold the molecules together enough to be a liquid, albeit very volatile liquids. Okay, you start getting up to diesel fuel, which is 19 carbons. That's not even flammable to, I mean, you can take a match and put it out in diesel fuel. Okay, you start adding more and more carbons onto the chain, and we start looking at things like wax, paraffin, asphalt, borrowing this again, plastic, right? My goodness, we got to a point where the alkane is a solid. Okay, and how many carbons did that take? Well, thousands of carbons in a row. So for our purposes, the general rule of thumb is the bigger a molecule gets, the higher its melting point is going to be, provided they contain the same functional groups. So if I were to compare octane to an alcohol, all bets are off at that point. All right? And we'll talk about why that is when we get to talk about alcohols. Now, for the last couple minutes of class here, I do want to talk a little bit about solubility. And I think that solubility is something that, well, it's something that I think is kind of intrinsic to us. We already know the solubility of oils, right? Think about it. What just happened in the Gulf Coast? Well, they had the storm. They had the oil rig release all from BP, all the oil being released into the ocean, or into the Gulf of Mexico. Okay, what happens to oil when you mix it with water? It sits on the top. If you ever take oil and vinegar, right? You make a vinaigrette, you shake it up, and then you let it sit for a couple minutes. What happens? It separates out. Okay, oil is going to be based on alkanes. It's greasy. Okay, would you expect oils to be water soluble or not? The answer is no. Do you expect alkanes to be water soluble? No. The reason for that being is that water is polar. It's held together by hydrogen bonds. An alkane is nonpolar. When it starts getting mixed up with the water goes, oh crap, my hydrogen bonds are breaking because this pesky alkane is sitting in the middle here. Let's push that alkane out so I can reform my hydrogen bonds again. That's why oil and water don't mix, because oil cannot participate in hydrogen bonding, and furthermore, it disrupts the hydrogen bonding that's already taking place in the water. Make sense? Okay, so that's going to be a rule of thumb that we're going to follow as well. There are two reactions that go along with alkanes. We'll talk about them at the beginning of class on Monday. You folks all go out and make sure you have a safe ride home. I understand that we have some nasty weather out there.